The last video illustrated a problem common to all amplifiers, not just to transistor ones. Because the output voltage Vout of the amplifier was sitting at a supply voltage VCC with no signal, it couldn't increase further when a signal was applied. The answer to this problem is to arrange in some manner for the output signal to sit halfway in between the positive and negative power supplies when no input is present. Arranging for this to happen is called biasing the amplifier, and this is illustrated in the diagram on the screen. This allows the output signal to move up to the positive power supply, which is called VCC in transistor circuits, and down to the negative one, which in transistor circuits is called VEE, as illustrated. As an aside, notice too that this type of amplifier turns the signal upside down. It is called an inverting amplifier. So how can we achieve this bias in practical terms? One possible way is to use a plus and a minus supply, for example plus 10 volts and minus 10 volts, and therefore the output voltage sits at 0 volts, which is in the middle. This would allow the signal to move up to 10 and down to minus 10. But this is often not practical, for example if we're using a battery. The more common solution is to arrange conditions at the input of the amplifier to result in the output being held at the correct voltage in between the power supplies. This is best illustrated with an example. Consider the circuit which is shown on the screen. So from our previous discussion, we want Vout to be halfway between the power supplies, that is, to be 5 volts, which is halfway between 10 volts and 0. Now to illustrate how to do this, let's choose a value of IC to work with. Let's say that we want to make IC 1 milliamp. This is a value which we just choose arbitrarily ourselves. And we'll see how to choose the values of components in the circuits to set this up. Firstly, if the output voltage Vout is going to be 5 volts, then the voltage across RC, the resistor in the collector circuit, is also 5 volts, because Vout is equal to the supply voltage VCC minus the voltage across RC. And since IC we've chosen to be 1 milliamp, this gives us a value for RC. RC is equal to the voltage across RC divided by IC, which is 5 volts divided by 1 milliamp, which is 5 kiloohms. But how do we get a 1 milliamp to flow in the collector circuit in the first place? Well, since IC is equal to beta times IB, and in this case beta is 100 for this particular transistor, we need to arrange for IB to be 10 microamps in order to get the 1 milliamp to flow in the collector circuit. Now remember that the base emitter junction is a forward bias diode, so it has about 0.6 volts across it. So we can calculate a value for the resistor RB to give a base current of 10 microamps, because we know both the voltage across RB and we know the current going through it. The voltage across it is the power supply, 10 volts, minus the 0.6 volts on the base, which is equal to 9.4 volts. So RB is equal to the voltage across it divided by the current through it, which is 9.4 volts divided by 10 microamps, which gives us 940 kiloohms. So we now have the amplifier which is shown on the screen. In practical circuits, it's also necessary to put in a couple of capacitors. The purpose of these is to allow the AC signal which we want to get into and out of the circuit, but to stop the DC bias voltages which we've set up from escaping from a circuit. That is the 5 volts on Vout and the 0.6 volts on Vin. If you're unsure about the role of capacitors in this circumstance, then review video 14. The values of capacitor can be chosen so that they have a much lower reactance than any resistances in the circuit. But very often engineers simply choose a suitably large value from experience. For example, at audio frequencies this might be a few tens of microfarads. The complete circuit is shown on the screen. You might also see a slightly modified version of this circuit, which is actually slightly better for reasons which we'll go into later on in the course. In this circuit, RB is connected to Vout, and the base of the transistor. And so the voltage across RB is Vout minus VB. This slightly modifies the circuit as shown on the screen. We'll find out more about these circuits later on in the course when we analyse amplifiers in more detail. But for now I'll just point out that they have a gain of a couple of hundred, that is a voltage gain, an input resistance of a couple of kiloohms and output resistances of 5 kiloohms. However, they also have a couple of drawbacks which I'll outline in the next video.